Multi-head attention, multiple perspectives. A single attention head tries to track grammar, meaning, and context simultaneously. It can't handle all three, and this isn't an opinion. It's a mathematical proof published at ICML in 2020. The solution turned out to be brilliantly simple, and half of it is redundant. Welcome to the 5th episode of the How AI Works series. Today, we take apart multi-head attention, one of the most important elements of the transformer architecture. I'll show you why a single head isn't enough and how a team of 8 parallel experts solves this problem. You'll also learn why researchers discovered that most of them are redundant. The real advantage of this mechanism is something entirely different from what you'd expect. At the end, we'll see how the mechanism evolved in just 8 years. Take an English sentence. The dog didn't cross the street because it was too tired. The model must solve 3 different tasks simultaneously. Coreference. The word it refers to dog, not street. Syntax. The subject-verb link connects dog with crossed. Semantics. Tiredness is the cause of no movement. A single attention head must choose one type of relationship. It's like one reviewer evaluating $1 million contract. They see either the legal aspect, the financial aspect, or the technical one. Never all at once. Vaswani proposed a solution in 2017. Elegantly simple. The formula that changed everything. Instead of one head operating on the full model dimension, Vaswani split it into 8 independent heads, each with its own set of 3 projection matrices: query, key, and value. Each head is a separate expert analyzing the same document but looking for something different. The formula is concise. Multi-head is the concatenation of results from all heads multiplied by the final matrix WO. Each head performs standard scale dot product attention, but in its own subspace. Here comes the key observation. In the original transformer, the model dimension is 512. 8 heads, each with a dimension of 64. 8 times 64 equals 512. The computational cost is identical. This isn't a trade-off. It's a pure gain in expression at no additional cost. 8 specialized perspectives for the price of one general one. The highway analogy captures this best. We have a road of the same width. We can send one gigantic vehicle down it, or divide it into 8 lanes and send 8 different types of vehicles in parallel. Grammar trucks don't block coreference ambulances. Semantics buses travel in their own lane. The road width hasn't changed, but throughput increased dramatically. BERT base uses 12 heads of 64 dimensions each. GPT-3, 96 heads of 128. Llama 2 with 7 billion parameters, 32 heads of 128. The formula, model dimension equals number of heads times head dimension, has not changed since 2017. The formula is simple. What the heads do with that freedom, nobody expected that. How data flows through multi-head attention. The full flow looks like this. At the input, we have a vector of dimension 512. This vector is split into 8 parallel streams. Each stream passes through 3 dedicated projection matrices: WQ, WK, and WV. 3 matrices times 8 heads. That's 24 learned projection matrices. Each head independently computes scaled dot product attention in its own 64-dimensional world. Results from all 8 heads are concatenated back to dimension 512. At the end, the final matrix WO integrates information from all perspectives. 2 key facts. Input dimension equals output dimension, 512. The model neither loses nor gains dimensions in this process. Computational cost doesn't grow with the number of heads, because each head's dimension decreases proportionally. Engineers designed this mechanism for computational efficiency. What they discovered surprised everyone. Experts who chose their own roles, Clark and colleagues published their findings in 2019. They analyzed 144 heads of BERT-based, 12 layers times 12 heads. They discovered patterns that nobody programmed. Heads spontaneously specialized in different linguistic functions during training. Syntactic heads track grammatical relationships with high accuracy. The best head, layer 7, head 6, achieved 34.5% accuracy in general dependency parsing. Other heads specialized in specific relations. A head in layer 8 tracked determiners with 94% accuracy. Positional heads direct their strongest attention to a token at a specific relative position. This happens in over 90% of cases, for example, to the immediate neighbor. These heads function as a local context window. The most fascinating are semantic heads. In the English sentence, the animal didn't cross the street because it was too tired. One head links the word it to animal. It resolves coreference at a distance. This is a fundamental ability. Without it, the model doesn't know whom a pronoun refers to. Another head at the same time connects because with tired, tracking the causal relationship. The model burns into the representation of the word it information from both sources simultaneously. Vojta and colleagues from ACL 2019 discovered something more. In the first layer, there's a head pointing to the rarest token in 66% of cases, and to one of the two rarest, in 83%. The model learned to identify words requiring special attention. Rare words often carry key information: proper nouns, technical terms, neologisms. Imagine a due diligence team evaluating a contract. The lawyer checks clauses, the accountant calculates financial risks, the engineer assesses technical feasibility. Each sees a completely different picture of risks in the same document. Nobody told them who looks at what. They specialized on their own during professional practice. Exactly the same thing happens with attention heads. Heads spontaneously specialized like a team of experts. Time to check how many of those experts are truly needed. From grammar to meaning, layer by layer. Head specialization isn't random. It follows a hierarchical pattern that mirrors the structure of language itself. Jawahar and colleagues from ACL 2019 demonstrated that BERT encodes linguistic information in an ordered hierarchy. Lower layers deal primarily with local syntax, positional attention patterns, tracking neighboring tokens, recognizing determiners. This is the foundation, grammar at the lowest level. Middle layers are the transition zone, syntactic chunking peaks. The model begins combining syntactic information with semantic information. Higher layers handle mostly long-range semantics, coreference, tracking acronyms to their full names, task-specific patterns. The boundaries between these zones aren't sharp. It's a gradient, not a strict division into three separated blocks. Higher layers still process some syntactic information. Kovaleva and colleagues from EMNLP 2019 identified 5 distinct attention patterns in BERT: vertical, diagonal, their combination, block, and heterogeneous. They found that less than half of these patterns are semantically meaningful. The rest are repetitive patterns that contribute no new information. What was discovered next redefines our understanding of the entire mechanism. Half the heads specialized. Time to look at the other half. Half the experts are redundant, and it's not a bug. Michel and colleagues published a shocking result at NeurIPS 2019. Up to 40% of attention heads in BERT can be removed during inference, without significant quality loss. Some layers can, in certain tasks, be reduced to a single head. Vojta and colleagues confirmed this on English-Russian translation at an even more radical scale. Pruning 38 out of 48 encoder heads, nearly 80%, resulted in a drop of merely 0.15 blue points, statistically insignificant. Specialized heads, positional, syntactic, rare word, are the last removed during pruning. The algorithm spontaneously recognizes their value, and the pruned BERT model achieves up to 17.5% inference speedup, practically for free. Here something more important than pruning emerges. The popular narrative says, multi-head attention provides multiple perspectives. That's why it's better. This narrative is repeated in tutorials, courses, and textbooks. It's also a myth. The paper Multi-Head or Single-Head published on Open Review proves this experimentally. Single-head multi-layer attention also attends to multiple positions and is even more parameter efficient. If multiple perspectives were the real advantage, single-head with enough layers should achieve worse results. It doesn't. The real advantage of multi-head attention is training stability. Multi-head achieves the same results using fewer layers than single-head. Less depth means easier training, fewer vanishing gradient problems, faster convergence. Research confirms a multi-head model converges more stably than a single-head model of greater depth. It's like dividing responsibilities in a team. It's not about the number of people, but that the division stabilizes the entire process. MHA isn't the magic of multiple perspectives, it's stable engineering. This engineering evolves. 4 generations in 8 years. MHA isn't the final version of the mechanism. In 8 years, it went through 4 generations, each radically reducing KV cache cost. The original MHA from 2017. Each head stores its own key and value vectors. With 96 heads in GPT-3, gigabytes of GPU memory during inference, a major limitation for production models. Multi-query attention, MQA, introduced by Shazir in 2019. A radical reduction. All query heads share a single key and value head. Inference speedup of 2 to 4 times. Palm and Falcon 7 billion use this variant. Grouped query attention, GQA, from Google Research in 2023. The golden middle. Divides query heads into groups, each group sharing 1 KV pair. Llama 270 billion uses 64 query heads with 8 KV heads. An 8-fold KV cache reduction at quality close to full MHA. Converting an existing model requires merely 5% of the original pre-training cost. GQA has become the de facto standard for production models. Mistral, Llama 3, and many other new models use precisely this variant. Multi-head latent attention, MLA, from DeepSeek in 2024. Compresses key and value into a low-dimensional latent space. DeepSeek V2 results. 93.3% KV cache reduction. Over 5-fold throughput increase. At quality surpassing standard MHA. From one overloaded expert, through a team of specialists, to an optimized organization. From 2017 theory to 2024 production. This is multi-head attention. What this means for your project. Let's summarize what we learned today. First, a single attention head has a formally proven rank limitation. MHA eliminates it by dividing the model dimension into independent subspaces at the same computational cost. Second, heads spontaneously specialize. Lower layers learn syntax, higher layers semantics. Nobody programmed this. Specialization emerges during training. Third, a large portion of heads are redundant. Up to 40% in BERT can be removed, and pruning delivers 17.5% speedup practically for free. Fourth, the real advantage of MHA is training stability, not multiple perspectives. This is a correction of a popular myth confirmed experimentally. Fifth, the evolution from MHA through GQA to MLA reduced KV cache by over 93%. Every new production model uses one of these optimizations. If this episode helped you understand multi-head attention, subscribe to the channel so you don't miss future episodes. In the comments, share which attention variant, MHA, GQA, or MLA, you use in your projects. In the next episode, we'll cover feed-forward networks, the knowledge store of the transformer. Feed-forward networks are the second key component, complementary to the attention mechanism. See you there.